Oh boy, got some new types of magnets. Something new to investigate. Please look at the information in the video description. Click Show More down below, and you'll see a lot of links and magnet-related info that people might not have encountered before. Namely, this company called CMR, Correlated Magnetics Research. Now we're going to compare what these magnets look like under what's called a magnetic viewing film. What this is just a green piece of paper with magnetically reactive fluid in here. So as you put it up to a magnet, you can see the line that separates the north from the south and all that stuff. So these are regular neodymium magnets. Let's see what this looks like under this viewing film. Again, you can see where I got this in the video description. The viewing films come from KJ Magnetics. These come from Correlated Magnetics Research. So, sorry about the glare. Focus. So we see that so-called magnetic line of force that separates the north and the south on a magnet. See that ring on the top, and we see the line in the middle. Alright, average magnet, north on top, south on bottom. So let's look at this one. Easy. North, south. We can tell this is a magnet. And wants to repel on the other side. Okay. So let's take a look at some of these new magnets. Now, fortunately, when I was playing with these when I first got them, I was forcing them together and doing the things that I was testing out, and one of these came unglued, which is good, so we can further investigate what this looks like. Anybody seen a magnet that looks like that? Multiple norths in a grid, multiple souths in a grid. Overall, this neodymium magnet is a magnet. See that line separating north from south. But in addition to having this being north and this being south, it has pinpricks of magnetism on it in a grid, so that when you have the inverse pattern approaching this magnet, it does something very different. So let's take a look at this. So we got this pattern on here, and this one on here. Let's put that back in there. So these magnets want to repel, but at the last second, you force them together, and then they click. They pass that point of force. And then you can lock them together. It takes a lot of force to get them out. Works the other way too. Repels, repels, repels. But you force it together, and they lock. And by having different codes of positive and negative, you can make it so that it's very difficult to do this, or it's very easy, or you can have them repel and then snap together, or you can have them attract and then at the last second repel, like this one. Positive, 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 positive. North, 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 north. When you flip it over, it's the same thing on the other side, but it's, see how thin that magnet is in there? This green film has to be right against the surface of the magnet in order to see the pattern. There's that like amount of plastic right there which prevents us from seeing that side. But if we look at the other one, we see that it has the same type of pattern in there. This one has nothing in the center, and then a ring of norths, and then nothing, and then a ring of norths. This one has stuff in the center, and then nothing, and then stuff, and then nothing. So it's the inverse. Watch what happens when we put it this way. Repel. And this way, it wants to attract, but at the last second, so imagine a cabinet door that goes together, but it doesn't make any noise, and it's sealed. It has magnetic, what they call attraction, but it's not touching. So it's called non-contact attachment. This way it just wants to repel. This way, weird. So imagine a ship docking doesn't need to have a rope tied to the dock. It just approaches, magnetically locks, but never touches the dock. Again, visit the information in the video description, because this has to do with Professor John Searle's technology. Yet again, John Searle claims that you can imprint magnetic bubbles or pinpricks of magnetism on the surface of a material. People have said that's impossible for decades. And then this CMR company comes out and starts imprinting pinpricks of magnetism on their materials, which we can plainly see it's not the same as a standard magnet. And when you do geometric ordering during a magnetization process and use different harmonics and different methods, you can achieve different things that normal magnets cannot achieve. So what would these do in a motor? Because normally you have to have a magnet flipping end over end in order to generate power in front of a coil. Positive, negative, positive, negative, positive, negative. But this one has multiple blotch walls on here. So what would that achieve? What can we do if we funded this type of research? Rather than furthering nuclear research, or obsolete oil, or dirty coal, gasoline, and all these obsolete things that we use today. Fund these type of methods that people don't know about and have said that is impossible. Apparently not, because I have this example in my hand. And I bet your average physics teacher and average science teacher has never seen anything like this before. Nor have they probably seen anything like the nitinol metal, shape memory metal. You stretch it out, get a little heat, it goes back to its original shape. So there's a bunch of things to look into that your average science teacher has probably never heard about. And when they say things don't exist, leave their classroom or challenge them right there. Because these things just need funding and resources to bring them to fruition. Rather than denying them, study them and experiment for yourself. Seek them out and play. Just play around. That's pretty much all there is to it. So visit the links in the video description, ask questions, and let's see what we can do.